In this lecture, we are going to see about what is tuned circuits. Tuned circuits are nothing but when some capacitor is added to a primary or secondary coils of a secondary of coupled coils, then it is called as tuned circuits. Actually, coupled circuits are used to transfer energy from one circuit to another circuit, and this is possible of transferring energy is only during the condition of resonance, and resonance condition is attained only the circuit is tuned. So tuning can be attained by adding a capacitor to the primary or secondary coils of the coupled circuits. Now let us see what is the difference between single tuned circuits and double tuned circuits. In single tuned circuit, when the capacitor is added to only to the secondary coil, then it is called as single tuned circuits. Whereas in double tune circuits, when the capacitor is added to both primary and secondary coils, then it is called as double tune circuits. So in our syllabus, we have only single tune circuits. So let us go through what is single tune circuits in this lecture. Single tune circuits. As we have discussed, single tune circuits are nothing but coupled circuits to attain it, to bring it to resonance by adding a capacitor to the secondary of the coupled circuit. So here they have added a capacitor to the secondary side of the coupled circuit. So this coupled circuit has become single tuned circuit. Now let us consider this JXL, JXL2, L1, JXM as omega L1, L2 and omega M, and JXC as J omega C. By considering this, we are going to apply KVL to loop 1 and KVL to loop 2, and we are going to proceed the single tune circuits. So by applying KVL to loop 1, what happens? E is equal to R1 I1 J omega L1 minus J omega L1 I1 and plus J x omega M I2 is equal to 0. It is written like this. Since current is entering to this and current is leaving through this, using dot rules, opposite sign for L and M, and you have obtained the equation like this, KVL equation. Now by bringing all the other terms to the right hand side, we have got our equation like this, and two terms I1 are common. So by taking I1 as common, R plus J omega L1 minus J omega M plus I2 is equal to, becomes the equation 1. So now by applying KVL to loop 2, so this is our loop 2. By applying KVL, minus from plus to minus, so minus J omega L2 I2 minus R2 I2 and minus of J by omega C I2 will obtain like this. And since this is minus, you will write this as plus J omega M I1. So we have written the equation like this, how we have discussed, minus J omega L2 I2 minus R2 I2, minus into minus becomes plus J omega by omega C I2 plus J omega M I1 is equal to 0. So here in three terms we have I2 as common. By bringing all those three terms together, we have obtained our equation 2. From equation 1 and equation 2, we are forming a matrix here. So for I1 term, and we have I1 term and I2 term. So for I1 term, you have R plus J omega L1, for I2 term minus J omega M. Here for I1 term J omega M, and for I2 term R plus J omega L2 minus J by omega C. Here you have E and here you have 0. So we have written like this. So from this matrix, we are going to find our determinant value, and we have to find only del I2. We don't need to find del I1 because in the secondary circuit only we have added a capacitor. So only we have to find what is del I2, and so to find the output voltage you need I2 into this value. So we have to find only this del I2. So first step we are going to find what is the determinant value. Del is equal to we know that we'll multiply the opposite terms, and we have written like this. Here no change in the first and second term, only this has been changed here to omega square and m square. Now by taking minus is common, I have written my del equation like this, so obtain my del value. Next, to find my del I2, I am writing my voltage terms E and 0 in my matrix form, and I'm going this into this becomes 0, this into this I have written here as minus j omega me. So to find I2 by Cramer's rule, del I2 by del is equal to this term, del term divided by your determinant value. I have got my del I2 value. But what happens here is, in single tune circuit, the primary inductive reactance must be negligible. So primary inductive reactance must be negligible, in the sense this value is negligible. So this term, this entire term R plus j omega L1 will be approximately equal to R1. Therefore my equation becomes like this. This minus and minus will get cancelled, so j omega me, this will become as R1. All the other terms will proceed in the same way. So I have obtained my I2. To find my, I have obtained my I2. To now I have to find my V0. V0 is equal to I2 into your capacitor term. So I have written my I2 term here, whatever I2 we have got, and my capacitor term. J and J will turn as 1, and then omega and omega gets cancelled. So my numerator will become ME divided by the entire term. So we'll see how the V0 has been obtained. So I have written the V0 as ME divided by C. All the remaining denominator terms I have written here. Now the condition says that at resonance the circuit becomes purely resistive. No more inductance or capacitor or capacitance should be in the circuit. So to attain that condition, we are taking this term to take this term, and we are equating it to 0 to change that as purely resistive. So this term, entire term R1 into omega RL2 minus 1 into 1 divided by omega RC is equal to 0. So by multiplying R here and R here and bringing this term to the right hand side, R and R will get cancelled. So omega R to L2 is equal to 1 by omega RC. So by cross multiplying this, the equation becomes like this. So from here, omega R square is equal to 1 by L2C. Therefore omega R is equal to 1 by root of L2C. So by substituting this value at my V0, the entire term, for this entire term, I have got this term as omega R. So by substituting this here in my V0, my new V0 voltage at resonance becomes ME by C R1 R2 into omega square m square. Similarly, my I2, whatever I2 I have got here, the entire term, this entire term will become as omega R square into m square. So sorry, omega R square into m square. So I have obtained my current I2 at resonance and voltage at my resonance. Now current I2 at resonance and voltage voltage at resonance depends on your mutual inductance and M coefficient of coupling A. So mutual inductance and mutual inductance coefficient of coupling K. So let us see that condition. The condition for maximum V0, maximum resonance voltage is equals to D of V voltage at resonance divided by D of M is equal to 0. So by substituting what is the voltage, what is M, here we have obtained the equation like this, but we are going to apply here our UV method. Using UV method, I have got my equation like this. So now R1 R2 omega R square m square is equal to M into, By substituting this in UV method, I have got this. So 2 into m omega r square. Now what is my r1 r2? This term will goes to my right hand side. So this entire term minus this term. This is m square omega r square. This is m square omega 2 minus 1 is 1. So from here, what is my m square? M square is equals to r1 r2 divided by omega r square. Therefore, my m becomes r1 r2 root of r1 r2 divided by omega r. But we know that our coefficient of coupling K is equal to m by root of L1 L2. Now I have got my coefficient. Now I can get my critical coupling Kc. Critical coupling Kc becomes this value divided by this value, m divided by my nu K. So root of r1 r2 omega r square divided by root of L1 and L2 is my critical coupling. From here my equation can be rewritten as critical coupling K is equal to 1 by omega r root of r1 divided by root of L1 L2. So this is how we have obtained the critical coupling for this condition. So we have just seen how a tuned circuit works and how tuning is attained using by adding a capacitor to the secondary of the coupled coil. So our syllabus has only single tune circuits, so we have seen how a tuning is attained in a single tuned circuits. Thank you.